Alright, thanks for watching. And today I want to prove the chain-rule in several variables. And don't worry, it sounds pretty horrible, but it's actually, in my opinion, one of the most beautiful proofs in math. And in fact, it will probably change the way you think about the chain rule. So again, not to advertise it too much, but I was transformed. Okay, let me tell you why. So here's some motivation. Suppose you have a function g that's a function of two variables. So g equals to not p but q. Again, it works for any number of variables. In fact, it also works for vector functions, so that's not a problem. So suppose g is a function of q, where q has two variables, q1, q2, and moreover, q is a function of p. So q is f of p, where I guess p is p1, p2. But on the other hand, q, you also have that it has two components. So f1 of p and f2 of p. So what you really have is that, let's see, so g, as I said, on the one hand, you can just think of it as depending on q1 and q2, but q1 and q2, they depend on variables p1, p2, and p1 and p2. Because on the one hand, g is a function of two variables, but each variable is a function of two variables. So this is, we want f of p1, p2, and f2 of p1, p2. And the question is now, well, g is a function of p really, because g is g of q, and that's g of f of p. And I'm using underline for boldface. And again, it's the same as g composed with f of p. And the question is then, what is the derivative of this with respect to p? So what is dp of g, which you may think of simply dp of a g composed with f? Well, let's just calculate it using the chain rule. And then you'll see, I'll show you how you can think of it as another way. So what is dpg? What this is, again, by definition of the gradient, that is partial g over partial p1 and partial g over partial p2. That's on the one hand. And now you want to think of it in terms of the chain rule. So you want to differentiate, first of all, g with respect to p1. So you do dg over dq1, dq1 over dp1. dg over dq1, dq1 over dp1. And then you do the same thing with q2, so dg over dq2 times dq2 over dp1 times dq2 over dp1. And you do the same spiel, but with p2. So dg over dq1, dq1 over dp2. So think of it as just a vector with two entries. So dg over dq2, dq2 over dp2. So, getting confused here. dg over dq1, again, first lot, and then dq1 over dp2 plus dg over dq2, dq2 over dp2. And now we can write it this way. Let's write it in a slightly more suggestive notation. Because remember, what was q? It was f of p, which was, f1 of p and f2 of p. So what this is, it becomes dg over dq1, df1 over dp1 plus dg over dq2, df2 over dp1. That's one entry. And then the other entry becomes dg over dq1, df1 over dp2 plus dg over dq2, df2 over dp2. It's normal I'm using this way because for variables I use subscripts. For like component functions I use superscripts. I'm not going to square or anything, don't worry. Okay, and so this is the form you usually use to. Now let me tell you the stuff that amazed me when I learned actually about this a couple of days ago, well, depending on when I make the video. But it turns out you can actually write this as a product of two matrices. So let me write you the matrix and then tell you what's going on. On the one hand, you can just think of it as dg dq1, dg dq2, and the other thing is df1 over dp1, df1 over dp2, df2 over dp1, df2 over dp2. Because just think of it in terms of matrix multiplication. dg dq1 times df1 dp1 plus dg dq2 df2 times dp1. Ta-da! First thing. And then dg dq1 df1 dp2 plus dg dq2 df2 dp2. Okay, turns out, again, think of what those matrices are. What do? You just take g and take the derivative with respect to all the variables. So that is dqg. So just the gradient of g with respect to q. And what is this? It's just the derivatives of all the f's with respect to all the variables. So it's literally the gradient of f with respect to p. And what did we try to calculate? dpg, which is really dp, g composed with f. So what does the Chen-Lu say? It says that the derivative of g composed with f, it's literally the matrix multiplication of the derivative of g times the derivative of f. Right? It's, if you want, think of it as follows. G composed with f prime. That's g prime at q. But what was q? It was f of p times f prime of p. So it is the Chen-Lu, except multiplication becomes matrix multiplication. Isn't that insane? Oh my God, it's like my whole life. I've been threw away 30 years because I've been thinking of the Chen-Lu in a wrong way. But it's really in terms of matrix multiplication that is the correct way. And as I said, here I just did scalar functions to simplify, but easily you can have just have G be a vector and it would still be a matrix multiplication. So this was the motivation. Now let me prove this to you. And as I said, the proof is much easier than you think. So that was actually harder than the proof. And for this, let me tell you some preliminaries about derivatives in higher dimensions. Because in single variable calculus, you just differentiate the function. You don't know what it does. But in higher dimensions, it turns out there's a nice definition for it. So just a little preliminary thing. Remember in one dimension, you had this linearization thing going on, or thing like Taylor polynomials. You have that, f of x plus h equals to f of x plus f prime of x times h plus higher order terms. So higher order terms, think like h squared, h cubed, etc., etc. So, in other words, to estimate f of x plus h, think like square root of 1.001, you start with f of x, add this derivative term, that is super important, times h, and you have sublinear terms, that are terms that sort of go to zero fast as h goes to zero. In multivariable calculus, it turns out you have the same expansion. Namely, if you start with a vector p and add a little vector v, you still have f of p plus the derivative of f with respect to p. Not that. It's like the derivative of f, but at p. Okay? And times v. So this is a matrix, or I guess a matrix or a vector, and you just multiply it by that vector, plus a remainder term. Let's call it Rf of v. And this remainder term, it's very small. It's what's called sublinear, namely, the remainder, as v gets very small, it goes to zero faster than v. So it goes to zero as v goes to zero. So some people derive it as little o of v. Okay. And notice again the similarities between the two definitions. We again have that f of a point times a small vector equals to f at that point plus the derivative of f at that point. I'm going to erase that. So plus the derivative of f at p times that vector plus a very small remainder term. And in fact, this is, if you want, the definition of the derivative in higher dimensions. It's any linear transformation, A, such that this whole gibberish holds. And it's what's called the total derivative, because it's totally awesome. Oh my god. Okay, good. And it turns out this is the definition that we'll use, and it becomes super, super neat. So, remember, we have three terms at hand. We have the derivative of f with respect to p, we have the derivative of g with respect to q, and we have the derivative of g composed to f with respect to p. So again, maybe let me box again what we want to show. We want to show that dp, g composed with f, equals to dp of f, no, dq of g, q of g times dp of f. So again, we have three terms at hand. The composed function, we have g and we have f. So let's start with dp of f. The definition is f of p plus v equals to f of p plus, again, dpf, so think of a, v plus the remainder term. And again, a is just, we just call it dpf. Again, think of a linearization. That's why sometimes derivatives are called linearizations. And now we can do the same spiel with q. Getting my terms confused. So with g, so dqg, what do we have? We have g of q plus w. That's gentleman's corridor. So g of q plus bw plus some remainder term, rg of w, where here b is dq of g. Okay, and what do we want to show? Again, for the 10th time, we want to show that dp of g composed with f is again, dq of g, dq of g times dp of f. And with our notation, we just want to show that it's BA. So, goal, what do we want to show? And again, we want to talk about dp g composed with f. We want the following expansion to be true. G composed with f of p plus v. Again, we want it to be, what happens if we start at p and we add a little v to it, we still want the original value, g composed with f of p, plus our derivative, which we want to be BA, v, plus a little term, like O of v, so a term that's sublinear. And so, once we've shown this expansion, we are done. So that's all we need to do, and I promise you it's really not that bad. Because what is this thing? G composed with f of p plus v. Well, by definition of composition, is g of f of p plus v. But again, we have an f of p plus v. So we actually can use this expansion here. So that's g of f of p plus av plus a remainder term, or f of v. And in fact, this little junk here, let's call it w. So w is av plus rf. av plus rfv. We'll need this later. Okay. But again, this is also nice because we have g at a point plus some junk. So now we can use the definition of g. So this is g of f of p plus w. And again, f of p, that's just q, remember. So q plus w. So we can actually use this expansion here. So this is g of q plus bw plus small term, or g of w. In fact, we don't need that now. Excellent. What's next is just unraveling all the terms. So gq, again, that's g of f of p plus b times av plus our remainder term, r f of v, plus the remainder of g, r g of w. And let's just expand it out. G composed with f of p plus bav plus b r f of v plus r g of w. Let's stop for a second. What have we calculated? We've calculated g composed with f of p plus v. And let's forget about this part here. No, super intense, like what's gonna happen. But look what we wanted to show. We wanted to show that g composed with f of p of v is g composed with f of p plus bav plus a small term. And look what we've achieved. We've shown that g composed with f of p plus v is g composed with f of p plus bav, great, great, plus this term. And all that's left to show is to show that this is small. So show that this is sublinear. Show that as v gets small, this whole thing gets small. You see how neat it is? We've barely done any thinking. We've just plugged in a bunch of stuff and used this linear equation almost. Okay, so now all we need to show is that, those terms are small. So first, let's deal with this thing. So BR f of v. So sorry, it's b times the remainder term. So it's a matrix times some term. Think of matrix as a number. It's like 2 times the first component plus 3 times the second component, etc., etc. You can just estimate it by just a huge number times this term. So it equals to some norm of b. Think like the sum of the values of b, or like the biggest value. Doesn't matter. All the norms are equivalent, times Rf of v. Okay. And again, what do we want to show? We want to show that this is sublinear, so smaller than v. So let's divide by v, and let's hope that this goes to 0. And indeed it does, because this is just a number. And remember, this term is sublinear in v. So it does go to 0 as v goes to 0. So this whole thing goes to 0 as v goes to 0. So in other words, this first term is in fact O of v. So BRF of v is O of v. And now we just need to show that this term is also small as v is small. And be super careful, because we know it's small as w is small, because it's the remainder from the expansion of g. And so what we want to do, we kind of want to divide by the length of w, but it could happen that w is 0. So we need to remedy this just a little bit. So, and for this, we use a sort of trick that was very similar to the proof of the 1D Chen-Lu. So just technicality. Again, because we want to divide by the length of w, which might be, 0, define. Let's see, E of w, to be the length of R of w divided by the length of w if w is non-zero, and else it's 0. Thinking calculus, you're just completing the whole. It has this removal discontinuity, and you just remove, add it back. Then what happens? Remember, we want to, I guess I erased it, but we want to estimate Rg of w, right? Usually you can just write it as Rg of w divided by the length of w times the length of w. As I said, sometimes it's a problem if w is 0, but even if w is 0, this is still defined. So instead of writing Rgw divided by w, we just use this E. And I want to emphasize it's on G, so Eg of w times w. Okay. And now let's just estimate our w, and remember w was there. So w, what is that? Length of w. Now come back to that. It's AV plus RF of v. And again, just use a triangle inequality. So AV plus this thing. And again, you can measure this by the norm of A, whichever you want, times the length of v plus the length of RF of v. And lastly, again, we can rewrite this term in terms of this error thing. So AV plus EF of v times the length of v. So W is less than or equal to that. And we'll come back to that. Now, let's go back to our Rg of W. And again, keep that in mind. We'll actually use it right now. So, Rg of W, again, we want to show it small if v is small, but this equals to, again, EG of W times the length of W, but this is less than or equal to EG of W times, so this identity, length of A, V plus EF of V times the length of V. And the nice thing is, there's a V now that comes out. Because again, we want to measure this with respect to V. So this is V times EGW V times EGW times the length of A plus EFV. Okay, so what do we want to show? Well, now, we want to measure this with respect to V. So RG of W, the remainder divided by V is less than or equal to EG of W times the length of A plus EF of V. And now the question is, what happens as V goes to 0? So if V goes to 0, first of all, remember what that was. That was essentially RF of V divided by V. And because, this is sublinear, this has to go to 0. Again, it's just a remainder of F with respect to V. Now, maybe this doesn't go to 0, yet it does, because now we use this identity, which is why I haven't erased it. If V goes to 0, well, this goes to 0, this goes to 0, and this goes to 0. So this whole thing goes to 0. So in fact, W goes to 0 as well. And because W goes to 0, again, by definition of EG, this also has to go to 0. So indeed, this remainder term, even though it doesn't depend on V, if V goes to 0, it goes to 0. So maybe, apparently it does then. And this is fantastic, because what have we shown then? If we put everything together, we get G composed with F of P plus V. Indeed, we have G composed with F of P plus BAV plus a sublinear term, which says, again, by definition of this total derivative, that the derivative of G composed with F is dA, which is dG composed with dF. How cool is that? We calculated, we proved the Chen-Lu without really doing any difference quotients or any weird limits. We just used this really neat formula and just expanded stuff out twice. And I feel it really explains, how the Chen-Lu comes up with composition, and it's interesting how matrix multiplication appears. So it's more powerful than you think. Alright, so if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.